In this video, we're going to see how sometimes the normal distribution can actually be applied to discrete data scenarios. So let's begin with example 1 that's in your notes. In example 1, you'll see a table of year versus a return as a percentage for an investment of a mutual fund. And it begins in year 1 and it goes all the way down to year 20. And respectively, there are return rates starting at 7.2% for the first year and going all the way down year 20, it ends up at 18.8. And what I'd like you to do is have Google Sheets open, because what I'd like you to do is to input, you can pause the video, and input this column right here into the spreadsheet. So perhaps what you might do is under, say, column A of your spreadsheet, start listing all of these values, and you'll have it beside row 1 all the way to row 20. So feel free to pause, go ahead and enter it, and you'll thank me later. Unpause when you're finished. What we're going to do is we're going to let the spreadsheet calculate a couple of things for us. We can do it by hand, but it's not as easy. If we want to do it by hand, the first thing we want to find is the mean. And you may remember that the mean is equal to the sum of all of the values divided by the number of values. So this one you could add all these up in your calculator, hit equals and divide by 20, and it wouldn't be so bad. If you did that, you would find you get 248.7 all divided by 20, which comes out to a mean of 12.435. And you might wonder why I've got mean shown this way, because today this mean is actually a sample, not a population, and this is the symbol we use for the mean of a sample. This is where the spreadsheet's going to come in handy, though, finding standard deviation. You may recall that the standard deviation, which we call S for a sample, is equal to the square root of the sum of all of the differences between every X value and the sample mean. Those take a long time to calculate and are easy to make a mistake of in your calculator, unless maybe you do a separate column and then add them all up. And then you have to divide by n minus 1 for a sample instead of just n. Okay, can be done by hand, okay, but it's easier instead if we use the spreadsheet. So I want to talk to you about how you would do it in a spreadsheet. What you would do in your spreadsheet is find another cell anywhere on that table. It could be underneath the table, maybe it's row or cell A21, or it could be one off to the side. And to find the mean, what you would type into the cell is, in Google Sheets, equals average, and then you would put a bracket and you would tell it which cells you want to find the average of. And in this case, you would be going all the way from A1 down to A20, and I would communicate that by A1 to A20. And you might say, well, Ms. Gerber, by the time I punch in all these numbers and I do all this, I'm not pushing fewer buttons. You're right. However, we're going to use the same column to do standard deviation too. Okay? So that's what you would punch into the cell. And when you hit enter, you actually do end up with 12.435. Now, in a different cell of the table, you can, maybe underneath here, maybe in A22, you might decide you want to find the standard deviation. So in that cell, you would punch in equals STDEV. That's what Google Sheets likes for standard deviation. Again, you would indicate from A1 to A20, or cell A1 to cell A20. And when you hit enter, it should pop out 9.49 for you. And that is so much faster than doing all of those things there. Okay? All right, so for that data set that's given in your notes, and I haven't filled in the values as I said, let's move on to the next question. It says, after we have discovered what the mean and the standard deviation are for that sample, we're going to assume a normal distribution. What is the probability that an annual return, so any one of these, could be at least 9%, which would be great, or they could be negative, which is kind of what we're experiencing in the world right now with our investments. So let's look at the first one. for the probability of it being greater than or equal to 9%, I'm going to choose again to use Google Sheets because I've got it already open. So remember, if we're going greater than or equal to 9, we have our distribution curve, and that means we're finding the area of the curve above a certain x value. Okay, in this case, our random variable x will be the return rate. So in order to punch it into Google Sheets, again, find another cell anywhere in your spreadsheet, and in that cell you'll type in equals 1 minus norm dist, and we've got the value of x, which is 9. We've got the mean, which is 12.435. We've got the standard deviation, which is 9.49, and then in Google Sheets we end with the word true. And when you punch that into that cell of that particular spreadsheet and you hit enter, you should end up with a value that's equal to, and I'm going to put it as a percentage multiplied by 100, it comes up to 64.1%. So you have a 64.1% chance over the course of those 20 years that an annual return will be at least 9%. Okay, that's not bad. What's the probability it will be negative? Well, if it's negative, that means that the probability is of x being less than or equal to 0. Okay, so we're going to do the same process, but because it's less than or equal to 0, let's just say 0 is here on this distribution, we are looking at the area under the curve here. So to program it in Google Sheets to do it for us, in any cell you wish, you would type in equals norm dist, the value of x, which is 0, same mean, same standard deviation, and end with the word true and your final bracket. That's what will go in your cell of your spreadsheet. And when you hit equals, and I'm going to put it into a percent multiplied by 100, you get around 9.5%. So that's a percentage chance of getting a negative turn in any 1 year, but when you're looking at a 20-year return cycle or investment cycle, that's not so bad. Okay, we could also use tables, but for the sake of time, I'm going to show you to use the spreadsheet instead. Okay, so the next question here says, out of the next 10 years, so if we went on from years 20 to 30, how many years would you expect to show returns greater than 6% if we're basing the behavior of this return on the previous 20? Okay, so we're looking at the probability for x being greater than 6. Okay, so again, to program it, we're going to realize it's a greater than, so it has to be 1 minus. So in our cell on the spreadsheet, we put equals 1 minus norm dist, and we'll put in 6, 12.435, 9.49, true, and we should end up with, oh sorry, it is, yeah, we did 1 minus, I got it. We end up with a value of 0.7517, okay, for this data set here. So if we're doing the next 10 years, we're going to take this probability and multiply it by 10. Okay, so 10 times 0.7511 would mean that we have a 7.5, or within years at year 7.5, between years 7.5 and 8, because this is x we solved for, we're going to get greater than 6%, and that's just based on how everything else played out. So we would get greater than 6% sometime between year 7 and year 8. Okay. Now, let's look at how the normal distribution can actually be applied to discrete data, but there's a slight adjustment we need to make when that happens. Okay. There's a beautiful picture at the bottom of page 1 of your notes to kind of show how this works, and it gives a bit of background that I think you can read on your own as well. I'm going to sketch the picture that I have for you in your notes at the top of page 2, where we have a discrete number line. We know it's discrete because it's made up of natural numbers or counting numbers, 1, 2, 3, 4, all the way up to 10. Again, this is just a sketch. You've got the picture in front of you. And what we're going to do is allow each one of these to have its own bin. Now, and that's how we can make it from being discrete data to continuous data. We can create intervals. Now, the thing is, we can't create the intervals right on the numbers like this, because we'll say, well, does that bin represent 2 or does it represent 3? So what we're going to do instead is we're going to create some bins that are in between each of these. So 0, 1, 2, and we'll let them grow upward as they would. And you'll notice that it peaks at 5 because 5 is the middle between 0 and 10. And then it will come back down. So you know, if we were to connect the centers of these bins and make a smooth curve out of it, you can kind of see this would look like a normal distribution, like this. And there you go. Okay. So the interesting thing about the normal distribution is that it doesn't work for finding instantaneous probabilities. In other words, you can't find the probability of just a single value. It's geared to find the probability within a range of data points. So we have to treat this as if it's continuous. So I can't say what's the probability at 6. Instead, I need to find the probability within that small range I've given it in converting it from discrete data to continuous. So, for example, if I want to know what the probability is when x equals 7, I'm actually going to find the area under the curve that corresponds to the area of this bin under the curve. Okay? And I would need to convert this from a discrete idea into a continuous idea. So this would become finding the area, or the probability, if you will, between 6.5 and 7.5. Okay? This adjustment that we're making right now is called the continuity correction. And we must do it before we solve any probabilities applying the normal distribution to discrete data. Let's look at a couple other examples as well. Let's say for this, I want to know what is the probability when x is less than or equal to 7. So what that means is I would actually want the number 7 to be included in the area under the curve. Okay, but I can't start at 7 because I'm going to start from either sides of these bins. Okay, so if I want 7 to be included because it's less than or equal to 7, I'm actually going to have to start here and do the area of the curve to the left of here. So this would become the probability of x being less than 7.5, you see. Okay, because it would be going in this direction. Let's look at if the probability of x is less than 7. Well, if it's less than 7, I don't need to include the number 7 in the area under the curve. So instead, if I'm going less than and to the left, instead of starting at 7.5, I can start at 6.5 instead. So we can adjust it to read the probability of x less than 6.5, and 6.5 is the x value we would use in our probability calculations. Let's look at another one. Let's say there has to be x has to be greater than or equal to 7. So here's 7, and I want to go to the right, and I want 7 to be included in the area on the curve. So I'm not going to start at 7.5 and go to the right, because then the number 7 will not be included. Instead, I'm going to have to start at 6.5. So we would translate and change this into the probability of x being greater than 6.5. I'm going to do two other examples that are not on this particular curve, but just to give you an idea. Let's say that you have the probability between x being between 50 and 75. Okay, so it doesn't even matter really what the curve looks like. How can we create a continuity correction for that? Well, if we think about the number line, and we have 50 here, and let's put, say, 75 here, and we've got bins at half unit intervals on either side of there. So 49 and a half, 50 and a half, I'll write those in. And 74 and a half and 75 and a half here. In this scenario, where are my start and end points for the range under some sort of normalization curve? Well, does the number 50 have to be included here? Does 50 have to be in it? The answer is no, okay, because x has to be, if you want to read it this way, greater than 50. So it's going to start here for finding the area under the curve. And if I want it to be less than 75, does it have to include the number 75? No, it doesn't. Okay, x has to be less than, so it would be here. So the area under the curve that I'm finding would actually range from 50.5 to 74.5. Okay, we ended up using the inside edges of those bins, if you want to think of it that way. What happens if I change this slightly and I say 50 has to be less than or equal to x, which has to be less than or equal to 75? And remember, when you're seeing this, this is for a discrete data set. It's not that a continuous data set couldn't have nice numbers, like maybe you end up being on 50.0, but I want you to realize this is with a discrete lens. How can we create an adjustment for it? Well, let's ask ourselves whether 50 and 75 have to be included in the area under the curve or not. Okay, so it says 50 has to be less than or equal to x, okay, or x has to be bigger than or equal to 50. So I want 50 to be in the curve, or be in the area under the curve. So I'm going to have to start at 49 and a half and go bigger in order to make sure 50 is included. Similarly, x has to be less than or equal to 75. So less than is this way. It has to include the number 75. So I'm going to start at 75 and a half. So my area under the curve this time, my continuity correction, will be the probability of 49.5, which would be less than x, which would be less than 75.5. Okay? So here's some great examples of how you can apply normal ideas, but you've got to bin, if you will, the discrete data because, as I said, the normal distribution is not designed to find the area of a line under the curve. It's meant to find a wedge or a section under the curve. So we have to give it a section to work with. Let's look at our final example and put this to a real-life scenario. So we've got a box of candy-coated chocolate pieces, and of course within the boxes you hope that there are whole pieces instead of partial pieces, and that's why you might see this as a discrete data set rather than a continuous, because you're going to be measuring, chocolates to the nearest 0.1 of a chocolate. The number of pieces in each box is assumed to be normally distributed. There's a mean of 48, and there is a standard deviation of 4.3. Okay, and what I should be doing here actually is, because we're taking samples off of the line, is I should be showing that this is a sample using this notation, and that the standard deviation S is here because it's a sample, not an entire population. All right, it says that as it's going through to the end, quality control at the end will reject boxes that have fewer than 44 pieces. And then boxes with 55 or more, quite obviously, result in costs to the company because you're giving away stuff for free, but you're paying to manufacture it. So the first question is, what is the probability that a box selected at random contains exactly 50 pieces? So you're trying to say P of X at 50. But you can't use 50 because we need to find the area on either side of 50. So immediately I'm going to change this into the probability of 49.5 being less than x being less than 50.5. Okay? So again, I'm finding a little narrow wedge, if you will, under that curve. I'm going to go straight to using Google Sheets because again, I'm assuming you have it open. So in Google Sheets, I need to take the area of all of this, subtract the area of this to get the difference or get that wedge. So I'm going to punch into any cell of Google Sheets equals norm dist, and let's find the area of the curve from 50.5 to the left and smaller. So x is 50.5, my mean was 48, my standard deviation is 4.3, and I write the word true to finish. I'm going to subtract the area of the curve from this point to the left. So norm dist, 49.5. I'm running out of room here. I'm just going to put it underneath. Sorry about that. 49.5, 48 for the mean, 4.3 for the standard deviation, and the word true to finish. And don't forget, when you're putting it into Google Sheets, you have to begin with equals, so it knows it's supposed to do a calculation. Now when you hit enter, you should end up with 0.0831. If you want to convert it into a percent, you can say 8.3%. So what they're saying is off the line, your percent chance of getting a box with more than the mean, okay, is only 8.3%, or getting exactly 50, okay? Let's go back to this assembly line, and what percent of the production will be rejected if it has too few pieces? So in the question it says it's going to be rejected if it has fewer than 44 pieces. So again, because this is a discrete data point, I have to give it a range to find the area under the curve of. So right away, I have to make my continuity correction. So we have to remember that 44 is okay. It doesn't get rejected. Okay, it says it gets rejected with fewer than 44 pieces. So 43 is not okay. So what we really want this to be is if we have 44 and we do our continuity correction of half a unit in either direction, we can do the area under the curve from 43 to and less. Okay, and then that will not include our friend 44. So we correct it to be probability of x less than 43.5, and we type it into Google Sheets as equals norm dist. We'll use our x value of 43.5. Same mean, same standard deviation, still ending with the word true. Again, this is going to give us, when programmed this way, the area under the curve and less, or under that data point and less, and we end up with a value of 0.1477, or if you want to, 14.8% would be fine as well. All right, now each filling machine produces 130,000 boxes every shift. How many of these are going to be lie within the acceptable range? Well, let's figure out what that acceptable range is. Okay, so just from the question, treating this as discrete data, we have the probability is that the number of chocolates has to be anywhere between 44 and 54, because it says boxes with 55 or more will be booted out. So 54 is the highest we can go. Okay, but we need to do a continuity correction for this because it's discrete. So how are we going to do that? Well, we want the numbers 44 and 54 to be included in the area that we calculate. So 44 and 54, if I have a bin on either side and I want to include these numbers, I'm going to have to go to the outer edges of that bin. So really, I'm going to have to go to 54.5 and to 43.5 as well to get the area between these two numbers under the curve. So my correction would be the probability of 43.5 less than x less than 54.5. So I'm going to have to do the area from here to the left, subtract the area from here to the left to give me the difference between them. So programming this would be norm dist for the higher value, same mean, same standard deviation, minus norm dist for the smaller value, 43.5. And when you hit enter in any cell of Google Sheets, it should yield you 0.7870, or if you want to see it as a percent, 78.7%. So this is the number, the percentage of all boxes that lie within the acceptable range. Well, how many boxes is that actually? Well, let's take our 130,000 and multiply it by 0.787 to discover that 102,313 boxes would actually lie within that acceptable range. Now, Part D says, if you own this company, what might you think about your current production process? Well, I'm looking at this going, only 78.7% of all my chocolates lie within my range. That means that about 21%, if I round this up, do not. That's way too many rejects, right? This is just above 3/4 good and 1/4 bad, okay? So what I need to do in order to make this better is I've got to make this standard deviation smaller. Because if I can make it smaller and closer to the mean, then I won't have as many rejects. So I've got to fix my packing equipment in such a way that this ends up being smaller. I need to redesign the line somehow, because somewhere along the line there's too much variance, right, from box to box. And there you go, normal sampling and modeling for discrete data.